All right, so in 6.5, we're going to start throwing some imaginary numbers in with all of this stuff as well, and talk about how we're going to graph imaginary numbers, and we're going to call them complex numbers. So we're going to learn how to plot complex numbers on the complex plane and find absolute values of complex numbers. Okay, and if you look at your formula sheet, there's a formula that says the absolute value of a complex number, and they give you a formula. So again, it's just using your formula sheet. We'll perform operations with complex numbers in the complex plane, and then we'll use the distance and midpoint formulas. Again, if you look at your formula sheet for distance and midpoint formulas, you won't find them on there because those are formulas that you've had since geometry. So we're not going to give you those two formulas. You'll have to, I guess, memorize those if you need to memorize those. All right, so we're going to start first with the complex plane. And the complex plane is really just your coordinate axis, but your x-axis now becomes your real axis. Put my pencil on. So if you look, this x-axis right here is the real axis. So that's where you'll plot the real part of your complex number. And do you remember when you have the complex number, and we'll use it with a letter z. So if the complex number is a plus bi, the real part is your a, and the imaginary is your b. So if you have a complex number a plus bi, then if you needed to plot it, it's just a point. You would just plot the same way you plot a point, where a is on the x-axis and your b is on the y-axis, but now the y-axis is like your imaginary axis. And then the absolute value of a complex number is really just the distance between the origin and the point, right? So if you think about it, if you have some complex number plotted, let's say we plotted this point out here, that was the point AB, because we had this complex number a plus bi. If we wanted to find the absolute value, or sometimes they'll call it the modulus, from what we're doing is finding the distance from 0, 0 to that point, which is really, if you were to draw a right triangle, you're really just finding the hypotenuse of a right triangle that has the base A and the height B. All right, so if we were finding that radius, we would just say the radius is the square root of a squared plus b squared. And if you notice, the absolute value formula has the exact same formula as the magnitude of your vector. Because again, if this was a vector, we'd just have this little arrow here. And if we found the length of the vector, we're doing the same thing. We're really just finding that distance from the origin. So when the complex number, the a plus bi, is a real number, so that would be when b is 0, then just keep in mind that your absolute value is just whatever the absolute value of a is. And because you're taking the absolute value, you should never end up with a negative. Your answer should always be positive. But again, if you're plugging it into that formula with the square root, you don't add the plus or minus in front because you didn't take the square root of both sides. You just take it for the fact that the formula is the positive square root, and so your answer is going to be positive because you're just talking about the length of something. All right, so in this example, it says find the absolute value of a complex number, and we have the complex number negative 2 plus 5i. So really what we're plotting is we're plotting the point negative 2, 5. So if you were to graph that point, and it's just a point, it's not a line or a line segment. So when you plot a complex number, you just plot the point. All right, this would be our complex number up there. So that's the first part. If you draw a line, now all of a sudden you've created something different. If we want to find the absolute value, remember to find the absolute value of negative 2 plus 5i, we use the absolute value formula, which is the square root of your a squared, so negative 2 squared, plus your b squared. So we'd get the square root of 4 plus 25, which gives you the square root of, 29. So then the next part is just operations with complex numbers in the complex plane. So if we need to add two numbers, this was a typo here. Let's make this x. Let's make that we'll make it a 2. Because otherwise we have to add them. So if you have to add two complex numbers, you're actually going to treat it almost like they're vectors. And this is where your vectors come in. Because when they tell you to do it geometrically, that means you might actually have to support your answer with a graph. Because first, if you were just adding these two things together, we already know how to add our complex numbers. You add your a's and you add your b's, right? So if we were to add these, we would say the complex number is 3 plus 4i. Right? We would add 1 plus 2, those are the a's, and then we would add 3i and I and get 3 plus 4i. But if we have to do this geometrically, then what you actually are going to do is to create two vectors with these components. And when you show that you've added these two vectors, they should end up at that same spot, 3, 4. Oh, I have two u's. So I should probably make that a v. Thank you. All right, so when you have to show that you're adding vectors, if we first start with vector u, right, that has the components of 1, 3. So if this is vector u, and then vector v has components 2, 1, which means we have to go what? Horizontally 2 and vertically 1. So from here, if we go over 2 and up 1, then from here to here, this would be like our vector u, and this would be our vector v. So it's when you add that terminal point with 1 and connect it to the initial point. And then that resultant vector from here to here has the components 3, 4. So when they ask you to do it geometrically, if you have to support it or you have to draw a graph, which is why I gave you graph paper, that's kind of what we're looking at, is putting those two vectors together and coming up with that resultant vector. All right, so we'll subtract these now. Right, so do you know, you can figure it out ahead of time what it would equal. Because if you subtracted these, you could do 4 minus 3 and get 1. And 2 minus a negative 1 would give you 3i. Right, so your answer should be 1 plus 3i. But if you have to show it geometrically, then we'll let vector u equal 4, 2. And we'll let vector v equal 3, negative 1. And if we want to subtract v, then we need to do the opposite of v. Right? So subtracting is like adding the opposite. So you have to figure out what would your components be for the opposite of v. And the opposite of v would be negative 3, positive 1. So those are the two we're combining. So if we start with vector u at 4, 2, and we draw this, and that's vector u, and then we combine it with the negative v. So horizontally, from this point, we have to go negative 3 horizontally, so 1, 2, 3, and then we have to go up 1. And so adding the opposite of v would be this vector right here. And so then that resultant vector would be from here to here. That's kind of what we just found, that 0.13. If that's something that you want to write on your formula sheet, so you have it on your formula sheet as you're doing your homework, you could definitely do that, because I'll give you just your clean formula sheet for your test and quiz. But if you don't want to have to keep referencing your notes, then maybe you want to add that to your formula sheet. And again, it's not on your formula sheet, so if you need to add it to your formula sheet just to have while you're doing your homework, that could save you some time from having to ask someone what it is or look it up, right? Because we know we don't like to look things up. I think that's all we have here.